says lesson 4, but of course that may or may not include some of the relative velocities that we do, that in another year I'll actually do this for a week and a half, if not 2 weeks, called vectors, right? But we don't have that much time this year. So whatever, I'm not counting, who cares? So mass and momentum are also relativistic, just like, what have we formulas for and what have we done? Well, we just had a quiz on time is not absolute. It varies depending on your frame of reference. And yesterday, which wasn't on your quiz, length. Well, why can't momentum be relativistic as well? And, well, it can, because there's the formula. It's actually on the back of your book too. But we ain't doing it. Okay? Just because. Like, we got enough. But let's just look at this. Now, momentum, as you know, if you recall, is a product of mass times velocity. Does that seem like 9.5 years ago you looked at a formula like that? Well, you know what? It's relative to your age, right? 1 month compared to your age is a lot larger percentage of your life than 1 month compared to me, because I've been around longer. I didn't hear that, but anyway. So it's all relativistic, okay? This is momentum. So you're saying, why is it different things? Like, it was time and time, we just had different times. Well, it says the same thing. That says momentum, that says momentum too. I don't know why we write it like that, but they did. I just want to inspect, and this applies to every formula, not just this one. We're telling you can't go at the speed of light, okay? We're just saying that you can't. Although we say if you could, time would stand still. And if you could exceed it, well, I guess time would go backwards. But let's just look at this formula. And by the way, these have been proven to be true, okay? They're not just theoretical. Took 20-something years, but eventually the world got around to proving these things, and yes, it does happen. What if the velocity is the speed of light? Well, what do I get in this formula? I get that, some momentum, it's got some mass, I don't know what, okay? And I got the square root of, if that is c squared, what's anything divided by itself? It's 1. And then what do I get? The square root is 0, which is fine. That's 0. But how many times does 0 go into, I don't care what this is, anything? We're telling you guys it's undefined, right? You can't do it. When I was a boy, they said it was infinity. That goes in there an infinite amount of times. So let's think of that. In other words, if you can go the speed of light, this says that the mass is infinite. And it doesn't really make any sense. And that's why you can't do the speed of light. In time, it actually does make sense, right? Because if the time is whatever TO was, some value, if this is infinity, that's an infinite amount of time according to someone on Earth. Which means, look at it the other way around, according to the guy in a spaceship, his time stands still, right? Does that kind of make sense? No? Yeah, well good. That's what I'm trying to do, is hurt your head. Okay? I'm not doing my job if I'm not. But it does kind of make sense. But infinite mass doesn't make any sense. Okay, so that's why we say you can't do the speed of light. You can go in 0.99999. This reminds me of gold, how pure it is. Anyway, you can do that, but you can't do exactly that. And as you know, the faster that is, well, the bigger that's going to be, right? The larger the mass. So, momentum is also relativistic. The faster it goes, the more momentum it has, because the larger the mass gets. Okay, anyway, let's move on. The most famous equation we know of. What is it? Yeah, and you knew that when you're 8 years old. You watched cartoons. But you had no idea what the heck it meant. And you might still not, but hopefully after today you will. That's the most famous formula there is, okay? And if you want to be really smart, you say it. And then someone says, oh yeah, what does it mean? And you go, I don't know. But what does E stand for? You've done this course. That's energy. If I spell it right. M is mass. Okay, and you might think, well, that's like units for a distance, which is a meter. Yeah, you're right. But this means mass. And now you know what C is. What's C? Yeah. In a vacuum. Squared. And someone just asked me yesterday, the grade 10 stuff, is that 16 or is that 64? Power raised to another power? It's 3 times 10. Well, it's that thing twice, okay? And then we add the exponents, yeah, 3 times 10, 16. Okay? So, all this is, like, how many variables do you have? You got that and you got that. The speed of light's a constant in a vacuum, 3 times 10 to the 8. So either, like this thing's pretty easy. There isn't much to it. Either I'm going to give you the energy and you calculate the mass, or I give you the mass and you calculate the energy. What units must mass be in? Yes. Okay. This is already meters per second. This needs to be in kilograms. Okay. So, and this has also proven to be true. There's this thing, particle, called a pion. And we know that's the weight of it. Okay, which actually is quite a bit heavier than an electron. And this thing has observed to decay, and it just kind of like, you can say vaporizes. It's there, and the next thing you know, there's a flash of light, and it's gone. And light is another form of energy. This thing decays into pure electromagnetic radiation, light, and this formula rings true. They measure the amount of energy that thing has. Maybe they got a little solar panel, collects that energy, converts it to a current, small, tiny voltage. I don't know how they do it, okay? But this amount of energy they got is exactly equal to this mass times the square of the speed of light. Wow. It works. So, if we could convert 1 kilogram of mass to pure energy, how much is it? Well, E is mc squared. 1, and I got 3 times 10 to the 8 squared, so that gives me what? 3 to the exponent of 8 squared is, 3 times 3 is 9, and 8 squared, 16. Now, what's the units here? Kilograms, meters per second squared, which is kilograms meters squared over a second squared. But isn't that energy? Well, remember, F is MA. 1 Newton is 1 kilogram meter per second squared. So that is kilograms meters per second squared times a meter, right? That is 1 Newton, okay? So that's Newton meters, and remember, work is force times distance. Yes, you do. Work is joules, and this is Newton meters, so 1 Newton meter is 1 joule. So this is energy. What units is energy? Don't worry, I'm not going to ask you to do that on the test. Okay, it's joules. I did. Okay, I'm proving it, all right? Is that a lot? Does it look like a lot? But like, what do you compare this to?
It's relative.
Let me show you. The average house, I just looked this up, okay? I was going to do cans of Coke, but even that's going to be a lot of cans of Coke, okay? What's relative? Do you want like power to like run your house? No. Okay? Well, but that's not even relative. What does that mean? You want to run your house for a month, okay? How much energy is that? To heat it, to light it. Exactly. That's why I looked it up. The average house in America is 1,000 kilowatt hours per month. What's that? What's a kilowatt? Well, that's 1,000 watts, right? So that's watt hours. What's a watt? Isn't that the definition of a joule? Or sorry, power. Watts is a joule per second. So that's 1,000 times 1,000 joules per second times hours. And then 1 hour is 3,600 seconds. So that is 1,000 times 1,000 times 3,600, which is 3.6 times 10 to the 9 joules. That's how many joules it takes to power the average house in America for 1 month. Let's do a year. Times it by 12, right? So then I have 3.6 times 12 is 4.32 times 10 to the 10 joules. How many of those go in here? Divide that by 4.32 to the power of 10, and that's 2 million houses for a whole year I could power with 1 kilogram of mass.
Sounds pretty efficient.
This, in my hand, actually the size of my fist if it were metal. If I can convert that to energy, I could power 2 million homes for a whole year.
A kilogram of what?
That's half a BC. 1 kilogram of anything. Anything. Peanut butter sandwiches. A golf club could power 2 million homes for a year. Now we know what that number means, right? Yes, you can. Well, we don't know how to do that yet. It's got to be a couple peanut butter sandwiches. But hey, give it a couple years. Maybe one of you guys will do it. Figure out how to do it. Okay, just do 1, 2, and 6 on that sheet. All right. Got 20 minutes to do her.